Welcome to the iLearn Virtual Campus. Please sign up for a free iLearn membership on our website. Check out our 7th annual conference coming next spring 2021, and let us know if you're interested in hosting events or leasing space on our campus by emailing campus@immersivelrn.org.
Session together with the authors. So enjoy the session.
Okay, hi everyone. Welcome also from my side. I'm Jens Kubert from Coburg University of Applied Sciences, and we will have 5 great papers in this session today. We will start with a paper of Matthias Kraus and colleagues, a comparative study of orientation support tools in virtual reality environments with virtual teleportation. And we will ask you to play this video now, please, and then afterwards we'll discuss this paper. Thank you so much.
Hello and welcome to my talk on our paper, A Comparative Study of Orientation Support Tools in VR Environments with Virtual Teleportation. For several years now, immersive analytics has gained in research interest, and more works appear every year. Also with regard to abstract data visualizations. While many of them can show, or most of them can show interesting approaches and opportunities of deploying AR or VR, the new technologies also bring some challenges with them. One of them is the discrepancy between real and virtual environments. Usually the physical available space is very confined, whereas the virtual available space can be designed arbitrarily big. So in case one needs more than space than the physical available, we have to come up with movement compensating techniques. Currently, the most popular movement compensating technique is virtual teleportation, where a user selects a location and is instantly relocated to that location. However, this sudden change might induce disorientation. Therefore, we wanted to investigate if we can provide additional visual tools to support the user maintain his or her orientation when teleportation is active as a movement compensating technique. In our study with 48 participants, we had 2 independent variables. The first one was orientation support tool. So we had 3 different visual tools that we compared to each other and to a baseline condition without any visual support. And this was between subjects, so every participant was doing one condition. The next one was task. We had a total of 4 tasks, which were done by each single participant. First, more detail about the support tools. In the non-condition, participants just could walk around and teleport around in the respective virtual environment without having any visual support. In the minimap condition, users had a minimap attached to the right to the left controller, and a small icon on the minimap indicates the rotation and the position of the player. In the tray condition, there is a line plotted behind the user, so when the user teleports or walks, the line is updated, and arrows on the line indicate the direction of how the path was walked. In the heat map condition, a heat map is plotted on the floor as well, indicating the previous locations where the user was. In the study, we had 4 different tasks and virtual environments. The first task was maze exploration. So the objective here was to find all markers where the users didn't know how many markers there were in the maze. On the right-hand side, you can see how the markers look like. So in the top, this is how the marker looked like when it was closed. And once the user approaches it and triggers it, it becomes blue and green. Here is an example of how this could have looked like in the minimap condition. So the user can use the minimap to navigate around and try to find as many as possible. The next task is a naive search task, in which the user has to collect all 4 markers and is aware of that there are exactly 4 markers in the maze. The next condition, it is the informed search task, where the objective was to find 3 markers but in correct order. On the right-hand side, you can see the closed marker, and once it's opened, it reveals a number. And we manipulated the markers in such a way that the first marker found would always display the number 3, the second always number 2, and the last one number 1. So once they reached number 1, they would have to collect the other 2 and would know their location already. So we could basically measure retrace performance. The last task, we chose a more realistic scenario instead of this orientation loss fostering maze environments, and deployed an industrial setting. Again, it was an exploration task, so the user didn't know how many markers there were, and they were just given the task to explore or to collect as many markers as possible. And we restricted the time to 5 minutes and decreased the size of markers. This is how it could have looked like. So you can see there's already 1 marker. There will be another one. It's actually very hard to recognize on the screen, but once you are in VR, everything is much larger and you can more easily identify them. Among others, we measured task completion time, task accuracy, spatial exploration, retrace performance, and memorization. We only considered the task completion time for the 3 maze tasks, as in the last condition, the time was restricted. And we can see that the known condition took in all 3 maze tasks much more time than all other conditions. When taking a look at task accuracy, which is in our case the amount of markers found in the 2 exploration tasks, we can see that the 2 techniques, trail and heat map, were better than the non-condition. So participants found more markers when being provided with a trail map visualization. Now let's take a look at spatial exploration behavior of users. For the 2 exploration tasks, we considered the area that was covered by the users. So how much of the actual accessible space was covered or visited by the users. For the maze exploration task, we could see that trail and heat map were better than the condition without any visual tool, and trail was even better than the minimap. For redundant visits, we tracked how often did participants stumble over the same areas again and visited certain places twice or more than twice. We found that for the naive search task, the non-condition was much worse compared to all other visual tools. In the third task, we measured the retrace performance of users. Participants had to find 3 markers in the correct order. So they would first find third, then second, and the first marker. And then basically when they reached the first marker, they would know the locations of the second and the third marker. Therefore, we could measure how long it took them to reach from 1 to 2, and on the right-hand side from 2 to 3. The minimap condition was in both retracings performing quite well and was significantly stronger than the non-condition. Now to memorization, we assessed after the 2 mazes how well participants could recall the ground plan of their respective maze. And what you can see here is that after the naive search task, which was the first maze, the large maze, participants could recall the maze best when being in the minimap condition, but also quite well when being in a non-condition. So without any visual tool available. It looks almost similar in the informed search. So for a small maze, even most participants could recall the ground plan of the maze when being in a non-condition. This is actually very interesting, as the trail and heat map conditions seem to have influenced negatively the memorability of users due to distraction. With these results at hand, we can conclude that in general, the provided visual tools increased orientation. The heat map and trail tools were relatively similar. They both reduced the amount of redundant visits, so participants saw where they have already been, and so they wouldn't walk again and again over these same areas. Also, they fostered exploration completeness, so they led to a more complete exploration of the available environment and seem to have improved the local overview, also of movement history. The minimap seemed to be best suited for retracing, as it provided the best global overview. Participants could, based on their current location and the location they have been before, optimally retrace to the desired target. And interestingly, memorability seemed to have been impaired by additional visual tools on the floor, trail and heat map, and participants could even better recall the ground plan of mazes when being in a normal condition. So without any distraction, they could recall the outline better. With that, thanks a lot for your attention, and I'm open for questions.
Okay, Matthias, thank you so much. I'm just looking into the audience. If there are any questions, feel free to use the chat, Buva, or you can also raise your hand. Let me just double check. And Buva, we have no questions. If we have other questions, not take your time. Matthias, I'll ask a question in between. So these orientation support tools that you've studied, they seem to have benefits and drawbacks dependent on the tasks that you conduct, right? If it's exploration, naive search, informed search. In many applications, those tasks change frequently. Yeah, given this dynamically changing scenarios and tasks, do you have recommendations on how would you recommend? Would you recommend to use one specific tool? Would you recommend to switch tools based on task or maybe other things? Can you speculate a little bit about that?
Yes, sure. So that's actually an interesting question. Thanks. What we did in the study was we picked out different distinctive tools and investigated them in separately. So what you could do, of course, if you have a very complex task that makes use of different of those sub-tasks, search, informed search, directed search, exploration, and so on, then you could also use a combination of all those techniques. So you could, for instance, combine heat map and trail, or heat map and minimap, and so on. So you could also create new mixed visual tools that could basically help you better in a combined task.
Okay, thank you so much. There's a question from the audience, from Bill Bernstein. I'm just reading it out. If I understood correctly, the occlusion of the support tools affects the navigation. How does that fact influence the findings regarding the efficiency of the guidance component of the tasks?
So if I understand correctly, you mean the occluding elements in, for instance, the heat map and the trail, but also the minimap maybe. Is that correct? Well, let's just assume that is. So
that's what I would assume. Yeah.
Yeah, okay. So I would guess for sure for some tasks, it might have a major influence on the actual task performance. As we also could see in the memorability performance of users, what we found was that actually the trail and the heat map negatively influenced their capability to recall the actual maze. So they didn't perceive the environment as they would have without any tool. So to overcome that, it might be reasonable to include an option to toggle the aids. So basically making them visible and then hide them again, and only display them when they are actually needed. So when the user takes them at a corner or something to reorientate.
Okay, so, great.
Yeah.
I think Bill Bernstein still, okay, yeah, he just said, thank you. Thank you so much. So if there are not any other questions, then let's thank Matthias again. Matthias, thank you so much. And we will go to the second talk, which is by Arafat Aziz, and it's called Haptic Handshake, a handheld multimodal haptic feedback controller for virtual reality. So please play this video, and afterwards we will have
Hello,
also
everyone.
questions.
My name is Arafat. Firstly, I would like to thank ISMAR for giving me the opportunity to present this paper. Our paper is based on a handheld multimodal haptic feedback controller device for virtual reality called Haptic Handshake. As virtual reality is gaining popularity, it has proven to be promising for a wide range of scopes, such as teleoperation, surgical training, industrial training, gaming, and entertainment. Today, we can find commercial headsets for a starting price of only $300, and the net worth of virtual reality gaming industry is forecasted to be about $50 billion within the next 5 years. Also, now that the pandemic situation has led everyone to carry out social distancing, I think that it is a good time for us to bring forward technology to improve touching and interacting with objects as well as people remotely. However, haptic sensations arising from touch are multimodal by nature. Therefore, if we ought to accurately deliver the sensations to the user's hand and fingers in a virtual environment, we have to provide a range of stimuli in the form of force feedback, skin stretch, vibration, temperature, weight, and so on. These haptic feedback can be modeled in real time by using position sensors to track hands and finger position, and then implementing actuators to deliver the haptic feedback. So, in order to deliver multimodal haptic feedback to the users, researchers have investigated and developed devices that broadly fall under 3 main categories, which are wearable fingertip devices, hand exoskeleton, and wearable haptic suit. However, these devices can be sometimes uncomfortable, cumbersome, or unsatisfactory for VR usage, mainly because they can convey 2 modalities of haptic feedback at max, and also the quality of the feedback depends upon the size compatibility of the user and the device itself. So, are wearable haptic systems really the best choice for providing multimodal haptic feedback to the users in VR? How about handheld controllers? Handheld controllers are great for VR. Why? Because with a remote in our hand, just with the press of buttons, we can switch between modes, pick up objects in VR, and also navigate very fast. Our hands can feel lightweight holding controller, which is really great for VR because we can throw our arms freely around. Also, we can integrate 2 such controllers to mimic different hand interactions, such as holding a gun or beating a hammer. If we were to use heavy haptic gloves in such cases, users will feel uncomfortable and tired after some time of use and feel reluctant to move or interact in VR ever so freely. Then, what is the shortcoming of commercial VR handheld controllers? Well, output is simply vibro-tactile feedback. Thus, in this research, we wish to leverage existing features of handheld controllers such as lightweight and comfort, and we wish to add 4 haptic modalities so that using our controller, users can feel harder soft objects in VR, hot or cold objects in VR, vibration of objects in VR, and users can also feel textures of objects in VR. How we achieve this will be shown in a short demo video next. The haptic handshake is a handheld controller device which can provide multimodal haptic feedback in virtual reality. The controller comprises of 3 modules. On the top, we have the thumb feedback module. In the middle, we have the palm feedback module. And in the bottom, we have the tracking module, an HTC Vive tracker which enables 6 degrees of freedom motion tracking in the VR scene. At first, let's take a look at the components of the thumb module. The soft silicon airbag sitting under the thumb pad is pneumatically driven by a pump attached to a control valve. It provides softness feedback during grasping. The thin membrane on the top of the airbag works on the principle of electrovibration. It enables texture sensation to the user's thumb. Thus, the thumb component allows users to feel the softness of virtual objects during grasping and texture during fine manipulation. The palm module comprises of 2 built-in devices for providing temperature feedback to the palm and fingers, allowing users to feel hot and cold sensations of virtual objects. Also, 3 vibrational motors are placed on the upper cap of the controller for vibro-tactile feedback. Thus, with the palm module, we can achieve a range of temperature sensations and vibrational patterns. Thus, by holding the haptic handshake, users can interact with virtual objects by grasping them to feel the temperature, rubbing with the thumb to feel the surface textures, pressing to feel the softness, and shaking to feel vibrations. So, as we have seen in the video, we embedded actuators inside the controller and exposed them to the user's palm and fingers to render haptic stimuli during interaction with virtual objects. After selecting the actuation method based on the spatial collocation of the hardware corresponding to the palm and fingers, the next step is to conduct experiments to determine the range of stiffness that can be simulated by the softness feedback module, the number of vibrational motors to indicate with the device, the number of peltiers to indicate with the device, meaningful vibrational patterns for VR application, and the best cooling technique for peltiers within the compact space. As I do not have much time left in this presentation, I'll provide a brief overview of the experiments and proceed towards the conclusion. In the first experiment, we determined the range of stiffness that can be generated by the softness feedback on airbag by varying the signal sent to the proportional control valve attached to the pump. So here is the experimental setup of the softness feedback module. Force reading from the airbag normal to the direction of elongation were read from the z-axis. The output from the z-axis were exported to an Excel file. So according to experiment results, we determined that the stiffness varies linearly between the voltage signal 0.05 to 0.18 volt when sent to the control valve, and we can simulate a range of objects with a target stiffness of 0.6 to 0.9 meter per millimeter corresponding to that voltage. Next, we did some experiments with operational motor for handheld controller in order to understand humans' perceptual performance of different vibratactile patterns. We had 4 distinct modes of vibrations. They were one at a time, upward vibration, downward vibration, and all 3 at once. Here is the experimental setup of the vibrational feedback. Subjects were given different tasks to distinguish between a combination of the 4 modes of vibration. From the result, we found out that using fewer motors and placing them farther apart in the controller can increase the identification rate between the tasks. Therefore, it is possible to provide directional cues in handheld devices using vibrotactile patterns. However, long-term training is necessary for improving the accuracy of identification. Next, we did experiments with peltiers in order to find out which method to choose for heat dissipation in order to achieve fast cooling. One interesting phenomenon about peltiers is that when there is difference in temperature between the 2 plates of the peltier, we can use this temperature gradient to generate electricity. This is known as Seebeck effect. So we include this in our experiment to see whether it is a viable solution for cooling or not. We repeated the experiment with 4 cases. Case 1 only had the peltier. Case 2 and 4 had heat sinks added. Case 3 and 4, we tried to harvest the energy by peltier cascading. Each experiment was repeated a few times to gather data. From the result on the graph, we can see that case 2 with only added heat sink allowed thermal energy to dissipate the fastest. Also, the standard deviation graph shows that cases 2 and 4 where heat sinks were added produced more reliable data. So we're using 2 peltier devices placed on either side of the controller. On the upper cap, we have 3 vibrational motors. The texture membrane, which is adapted from our previous work called Flex Touch, is glued to the top of the silicon airbag. We implemented a PI controller loop to control the temperature of the thermal feedback to the palm area, which is the most sensitive region to the temperature change. And at the bottom, we have a 6 degree of freedom tracker that senses the motion of the hand. We designed a custom PCB to control the actuators. We deployed real-time operating system to schedule tasks and send control signals based on priority. We placed the PCB and the control hardware outside of the controller to save space and make the controller more ergonomic in shape. The control theory of the hardware and the limitation of the actuators are presented in the paper. With regards to controls, our controller is a simplistic handheld device. Yet, users can have an immersive experience in VR. It has the ability to render temperature within the range of -26 degrees Celsius and switch from hot to cold within 9 to 13 seconds. Softness feedback display can render stiffness up to 0.9 meter per millimeter square. Textile membrane can deliver a maximum frequency of 1000 Hz, while the vibrational motors can generate a vibration of up to 90 Hz. In conclusion, we have designed a multimodal handheld haptic feedback controller that can provide softness and texture feedback to the thumb, as well as temperature and vibrational feedback to the palm and fingers. The preliminary demo suggests that the device is promising for handheld VR application. Although there is a very big room for improvement, we hope our device can spark more interest in the field of multimodal haptics. I thank you all for listening to my presentation, and your questions are most welcome.
Okay, Arafat, thank you so much for giving this presentation. And I'm just looking into the audience if there are any questions. In Ruba, we had no questions, I guess. So if you have any questions, feel free to either raise your hand or to type them in the chat. Arafat, I have a question in between. First of all, this seems like great engineering work. You surely put in quite some effort. I wanted to know, you showed one VR scenario showing having this cup. Did you actually investigate further scenarios, further objects in VR apart from that cup example? Or specifically, could you maybe speculate for which scenarios or objects your device would be suitable, very suitable, or less suitable?
Thank you for your question. Actually, due to the because right in our lab we do not have the opportunity to explore more and more opportunities due to the restriction of the coronavirus. So this is why we only had the opportunity to create one demo. But I think in terms of surgical simulation, it is possible to create more application, and also for gaming and entertainment.
Okay, so then we have a question from the audience, from Victor Mersado. What is the difference between your approach and passive haptics?
Actually, this is mostly passive haptics because we have used some kind of commands to send to the different actuators to create the haptic feedback. But I think in the future we would rather explore more active way to control the hardware, like actuators. So it's mostly passive feedback.
Okay, just looking at the other questions. Victor says thank you, and maybe I have one more question. It was in your paper. It was evident that the engineering world was quite big, and you also used, I would say, rather demanding devices. Do you have any ideas how you would continue your work to come to a more mobile implementation that could be also used outside of lab environments?
Yes, I think that some of this hardware is very heavy. For example, we were using the pump, but it is possible to use a miniaturized pump, and also for the heating, we could implement much better cooling technique, for example, liquid cooling. And also for softness feedback, I think in the future it is better to use some kind of pin array or magnetorheological fluid so that we can render more softness in the sense of, for example, we can render some kind of shapes as well.
Okay, then thank you so much. I'm just looking to the audience once more. If there are any questions, I can't see them. So then let's give Arafat a hand. Thank you so much. Okay, sorry. Actually, there was one question, but maybe you can find Arafat just after the talk, because we need to continue. And Arafat, I will forward that question later on for you. So let's now continue. We have the next talk by Wujin Chu, which is called Bare Hand Depth Inpainting for 3D Tracking of a Hand Interacting with an Object. So let's take it away.
Hello everyone, this is Wujin Chu from KaiST VR Lab. Today I'm going to introduce my work on the hand pose estimation. This work has been done with Gabyong Park and Untitled. As the augmented reality technology evolves, the need for natural hand gesture-based interactions is growing. A real-time hand pose estimation can further develop the hand-based interactions. Although extensive studies have been conducted on the isolated hand pose estimation, tracking of a hand interacting with an object had relatively less attention and remained as a challenge. Our aim is to achieve robust 3D hand tracking for a hand-object interacting scenario with RGB and depth images. There are several challenges for this objective, like self-similarity and occlusion of the hand itself with the highly articulated joint structure of the hand. And in the object interaction scenario, we also need to consider the occlusion by the object and various object types. Most previous works tackle this problem by training with a dataset that includes objects, or utilizing object information for pose estimation. These works were effective in some constrained environments, while including a vast feature of objects in the latent space to be run, or performing an additional process to utilize information about interacting objects. Related to our approach, Generative Adversarial Network GAN has utilized in various research fields, and few studies have adopted them for hand pose estimation. For example, the first one they utilized GAN to synthesize highly realistic and accurate depth maps of the articulated hand during training step. And the second work utilized GAN to generate a realistic dataset that can reduce the appearance gap between the synthetic and the real hand. The last one generated a depth map of the hand from a hand-only RGB image. These works indicate that mapping to bare hand depth images is sufficiently reliable and effective. Our key idea is that 3D hand pose can be relatively easily obtained by generating bare hand depth images from RGB depth input. As we need to maintain the articulation of the hand, we inpainted bare hand depth image using a conditional GAN with image level supervision. To train the generator as our purpose, we constructed a new paired dataset by synthesizing an arbitrary 2D silhouette of the object on the bare hand dataset. And we utilized RGB data as an indirect segmentation cue for objects and hand, which makes it possible to omit the segmentation process from the entire system. For our generator, we adopted previous work about image-to-image translation. After the training step, the generator directly performed as a preprocessor for the bare hand tracker, which let us utilize the bare hand tracker in the hand-object interacting scenario. The hierarchical particle filter from previous study has been adopted for the tracker. The loss function for training has been determined as shown. We induced the generator G to produce corresponding bare hand depth image and discriminator D to determine whether the generated image corresponds to a bare hand image or not. The objective contains three types of term: conditional adversarial loss, context conditional loss, and error norm loss. The conditional adversarial loss was applied in the form that was used in the past, and the context conditional loss induced a stronger running effect for the reason occluded by the object. Lastly, the traditional error-1 loss has been adopted with conventional knowledge to induce the generator to be near the ground truth. As mentioned earlier, we required a paired dataset consisting of bare hand and object hand pairs for direct image supervision. At this point, we observed that although the 3D geometric form of the object may vary, the 2D silhouette projected by the camera was significantly less diverse. So we decided to utilize the 2D silhouette of the object rather than augmenting 3D objects. The dataset was generated by overwriting random polygon, texture, and randomly positioned depth map in the identical pixels of the bare hand images. Of the art, which states that the proposed approach successfully generated an effective bare hand depth image from the unseen data, and that the post record performs well even though it was designed for the bare hand situation. Qualitative experiment was conducted for the Dexter HO and self-generated sequences. The total runtime of the proposed method was 32 milliseconds on a single GPU, which satisfies real-time performance. You can find some erroneous frames that fail to generate bare hand completely, but it still demonstrates that these incomplete depth regions can serve as an adequate cue for the bare hand tracker. Also, considering that the trained dataset consists of the arbitrary 2D silhouette, our approach succeeds to produce effective bare hand depth image for real objects. In summary, we presented a novel approach for the 3D tracking of a hand interacting with an object that utilized the conditional GAN to generate bare hand depth image. We showed that the dataset with synthesized 2D silhouette can affect generalization for various daily objects. Through the approach, we demonstrate that bare hand tracker can perform comparable results to a state-of-the-art that designed for hand-object interacting scenario. Still, it shows limited performance in hand-only or highly occluded poses. And the synthesized dataset falls short real-world object interacting pose distribution. Also, the in-painting results lack temporal continuity as an image was generated regardless of the previous frame. This can be further developed by adopting a semi-supervised learning technique and leveraging advanced GAN to perform an enhanced cross-domain transformation. Thank you for listening.
Okay, then Woojin, thank you so much for presenting this talk. I'm just looking if there are any questions here from the audience. Not yet, so feel free to state your questions. So I have a question. First of all, it's very nice work. My question would be, would your approach also be feasible for hand tracking of for other hand poses? So because you were mostly showing, let's say, the palm, specifically, you mentioned it already, in presence of self-occlusions of either multiple hands or individual fingers. And I think you already stated it a little bit, but can you speculate a little bit more about how your pipeline would need to be adapted to also cope with these self-occlusions of fingers on both hands?
Yeah, thank you for the question. For that point, our system generates the purpose of our system is to generate the bare hand depth image, and the tracker has been just adopted from the other research, for this case, the hierarchical filter, particle filter. And as we've shown, we still lack and some showing good results in various poses, but could be developed more by adopting some highly developed bare hand tracker, and just wanted to show effectiveness of the depth in painting.
Okay, thank you so much. Are there more questions for Wujin? Either you can raise your hand, we're not so many here, so you could also just try turn on your microphone if there are any questions. If not, then Wujin, thank you so much for that great work, and please continue working on that. Thanks so much. Let's give Wujin a hand. Okay, so then we will have the next talk presented by Eileen Ricker, which is called The Influence of Hand Visualization on Tool-Based Motor Skills Training in an Immersive VR Simulator. So let's listen to her talk.
Good morning to everyone. My name is Eileen Rica. I'm a PhD student at the BISC laboratory of the Paris-Saclay University. And today I will be presenting our work, which consists on studying the influence of hand visualization on tool-based motor skills training in immersive virtual reality simulators. Nowadays, we see that immersive virtual environments are increasingly being used in different domains. Not surprisingly, skills training in such systems has been shown to be very promising. Flight simulators are a clear evidence of the success of immersive technologies. Today it's compulsory for pilots to train and validate their skills in a simulator prior to stepping foot inside a real plane. Maintenance industry is also adopting virtual and augmented reality systems to provide a controlled and safer training. And in the medical domain, we can see several approaches to use VR simulation for resident students training. Most of these immersive VR simulators require the users to wear a head-mounted display and allow them to explore the virtual environment from a first-person perspective, but without seeing their own physical. So one open research question in the development of such systems is how the user's self-avatar is represented inside the virtual environment, and which is the impact that this representation may have on the user's performance. We can define the self-avatar as the visual representation of the user's body inside a 3D environment. Well, in this work, the focus is made on the design of VR simulators for training fine surgical motor skills. A fine motor skill or dexterity is the coordination of small muscles in movements usually involving the synchronization of hands and fingers with the eyes. And well, examples of these fine motor skills are instrument handling, tying knots, suturing, cutting, or many other surgical procedures. And well, for those fine motor skills, the self-avatar representation concerns primarily the user's hands. Well, the importance of body-based perception in immersive environments has been studied for some time, showing that there is a high correlation between the sense of presence and the degree of association with the virtual body, which we call the sense of embodiment. Experiments based on the rubber hand illusion show that if the user is presented with a conflict between the visual and proprioceptive position of his hand, he will prioritize the visual over the proprioceptive position. Well, human motor skills can also be influenced by visual feedback. Previous work have shown that the size of the virtual hand can influence performance, particularly when the hand is controlled by the user, and also that the kinematic fidelity of the avatar is significantly more important than the visual fidelity for direct manipulation tasks. Well, as we can see, research has focused on studying the influence that hand appearance and structure may have on the user's sense of presence and embodiment. But little is known about the role it plays in learning motor skills, in particular for tool-based motor training. So in this work, we investigated how the user's performance is influenced by the real hand movement representation when performing a tool-based motor task that is inspired by existing surgical skills. Well, to answer to our research question, a VR simulator and a user studies were designed, implementing a simple pick and place task. We formulated two working hypotheses for our study. Previous research suggests that adding virtual hand will increase depth perception and give users additional special cues when manipulating tools. Therefore, we expect that the presence of the hand will improve the user task performance, which we measure as the task completion time, the accuracy, and the errors. Besides, previous work have shown that the user sense of presence increased with the self-avatar representation for tasks involving direct manipulation of objects. So we expect that this is also the case for tool manipulation tasks. Well, as I mentioned before, we have designed and implemented a VR simulator for a tool-based pick-and-place task. It consists of a VR application using two haptic devices, which control the two virtual tools, and also provide force feedback for the collisions of the virtual tools with the virtual objects in the scene. Well, this interface also had a 3D printed forceps attached to simulate the opening and closing of the tool. The user was immersed in the virtual environment thanks to an HTC Vive head-mounted display, and their hands were tracked using the High-Five data gloves, which allowed us to animate the fingers' positions and flexions of the hand inside the environment. Well, the virtual environment consisted of two forceps tools controlled by the user with the haptic devices, 6 pickable cubes, and a working space divided in two by a rigid wall. 6 square targets were also designed in this working space. Well, the task implemented consisted of picking up a cube with one tool, change it into the other tool in the exchange zone, and place it in the target square with that tool. At the beginning, the 6 cubes were placed, 3 at each side of the wall in the initial zone, and the target square were also designed 3 at each side. Both the initial cubes positions and target squares were numbered, and the user was asked to place each cube in order and in its corresponding numbered target. The experimental design followed within subject design with two conditions: the presence of the virtual hand and the absence of it, which means only visualizing the virtual tools. A total of 40 participants were enrolled. They all performed 3 trials of the pick, transfer, and place in each condition. They were asked to place the 6 cubes as quickly and as accurate as possible, all by avoiding tool wall collisions and dropping the cubes during the task. The order of presentation was counterbalanced to avoid any learning effect. And after finishing 3 trials for one condition, participants were asked to answer to a state of presence questionnaire. And at the end of the experiment, we evaluated the perceived system usability of the whole system. Both objective and subjective measures were collected. The results showed that there were no significant difference between the two conditions for any of the time, accuracy, and error measures. In addition, we used Pearson and Spearman's correlation test, as well as equivalence test, which showed that regardless of difference in personal abilities between participants, moderate and high correlations were found, which suggests that the participants reached the same task performance for both conditions. The subjective analysis of the presence questionnaire reported that the virtual hand elicit a higher sense of agency than the tool's only visualization. No other difference were found for this questionnaire. And in addition, no measured difference were reported concerning the preference of the virtual hand. Finally, the system usability questionnaire reported a mean score of 74, which encourages the choices made for the design of this VR pick and transfer trainer. Well, as I presented, no difference were found for any objective measures. Indeed, the high to moderate correlation was found between the conditions for all the measures. Well, a possible explanation for this finding may rely on the fact that for our pick and place task, the users were holding the physical handlers during the whole experimental session. This might have generated a form of embodiment beyond the body itself, allowing the participants to include the tools as if they were part of their body, as if their hands were elongated to the extremity of the tool. In this case, the users were focused on the tool tip visualization rather than the hand visualization. Well, as a whole, these results suggest that the visualization of the user's animated hand is not necessary to perform a simple tool-based motor task in a VR simulator. However, other studies are needed to generalize these results to other motor skills and VR simulators. Indeed, it would be interesting to study in the future the impact that hand representation can have in the absence of haptic feedback, as well as while using purely virtual tools instead of physical ones. Finally, concerning motor skills training, here we only study the effects of hand visualization on performance in a single experimental session. In the future, it will be also it will also be interesting to see if these results also apply when the user trains for a longer period of time in the simulator, and whether training under each condition has the same impact on the transfer of skills to the real world task. Well, thank you for your attention, and I will be happy to take questions.
Okay, Eileen, thank you so much for that very interesting presentation, that very interesting work. I'm just looking into the audience if there are any questions right now for Eileen. If not, take your time. I have a question for you. So that was a tool-based task, right? And the important actions, as we saw it, they happened at the tooltip. And this tooltip, or the distance between the tooltip and the actual hands, it was rather large, at least from the video. Could you speculate maybe a little bit if and how the results might change, or maybe also not change, when other tools are used, maybe where the action is happening closer to the actual hand?
Yes, well, the large distance between the tooltip and the hands it's related to the fact that we are using haptic devices, so it was hard to choose an intermediate point, and we were also simulating a real task for further studies to compare the transfer to the real task. So we were using the real forceps tool measures. Yeah.
Oh, okay. Yeah, please go ahead.
Yes, maybe if if we run this study in another type of tool which is closer to the hand, the results could be different. Yes, of course.
Yeah. Okay. So we have a question from the audience, from Florian Heinrich. Do you have experience with different hand tracking devices, such as gloves, and did you vary the displayed hand size with respect to the participants?
No, for this study we used a generic hand model. That's why maybe we didn't have a significant ownership results from the participants. But yes, it would be interesting to see if the appearance fidelity of the hands may influence the results. For this study, we used only high five data gloves. We did a previous test with lip motion, but since we are holding a physical tool, it was hard to get the real posture of the hands and fingers during the simulation due to occlusions.
Okay, thank you so much. I'm just looking into the audience one more time if we have. Yeah, there's one more question. So, did you differ between age and gender of participants? By Bianca Jürgens.
Yes, well, participants' age range from 18 years old to 40 years old, and They were general users, no expert with no expertise, with not much expertise with virtual reality, and we also equilibrate between males and females during this experiment.
Okay, so then thank you so much. I'm just looking one more time. Is there any further questions? If this is not the case, then let's give Aiden a hand. Thank you so much. Okay, and then we will come to the last talk of the session by Brett Bender, which is called Determining Detection Thresholds for Fixed Positional Offsets for Virtual Hand Remapping in Virtual Reality. So then please play the video, and afterwards we will have questions. Thank you so much.
Hello, my name is Brett Benda, and I am a PhD student at the University of Florida, and I'll be presenting our work. In virtual reality, hands are often a user's primary means of interacting with their environment. Normally, virtual hands, or the hands you see in the virtual environment, are located in the same place as a user's real hand or controller. But sometimes, VR designers want to allow users to reach virtual objects beyond their physical reach, or realign their physical position to their location in the real world. Hand remapping techniques have been developed to achieve these goals, such as the go-go technique, which extends a user's reach, or translational and interpolative reaching, which slowly adjusts a hand's location towards a physical target. These techniques displace the user's virtual hand from the location of their real hand, which can become noticeable if applied to a large degree. If a remapping technique is applied at a large enough magnitude, the user may notice it is being applied, which can be distracting in environments where immersion is key. However, estimations for these magnitudes can be determined using a psychophysical method, which provides us with a threshold value for the technique. If we stay within these thresholds, most users will be unable to detect. These psychophysical methods often utilize a two-alternative forced choice design, where users are exposed to varying levels of a technique to gauge their perception. These methods have been used extensively in determining thresholds for many other interaction techniques, including gains applied to a user's path in redirected walking and multiple forms of hand remapping. However, no prior work has examined fixed offset transformations to hands, where virtual hands are displaced a constant amount, regardless of the physical hand's movement. By examining these types of transformations, we are able to provide guidelines for maximum acceptable displacement users experience during other techniques, where the virtual hand placement may be modified continuously. In this animation, the gray hand represents the user's real hand, while the blue hand represents the virtual hand they see in the virtual environment. As the hand moves, the virtual hand relative orientation stays constant compared to the real hand. Our work is summarized by our two research questions. What are the maximum constant offsets that can be applied to a user's virtual hand in each direction before it is perceptibly not normal? And how do they differ from one another? And our second question, how does offset direction and magnitude affect target selection? We examined two offset characteristics, the direction relative to the user's forward direction, and magnitude, or the distance between the virtual and real hand. We employed a within subjects repeated measure design in our experiment and collected data from a total of 19 participants. We designed an experiment that would require a range of possible movements, with our goal being to estimate thresholds while users were performing movements they may use during general application use. We placed 8 targets in front of the user, located on the corners of an invisible cube, which had its position calibrated for each user to maintain consistency. Users then experienced each offset in a random order, and while each offset was applied, the targets appeared randomly and users were asked to touch them as quickly and as accurately as possible. After touching the final target, users were asked via a virtual interface if the hand placement felt normal or not normal, and provided an answer with the controller. Users then returned to a neutral position and began the next trial with a new offset. Based on our participants' responses and the data we collected, we first fit curves for each direction to predict when users would feel the offset was normal or not normal. From these curves, we were able to determine detection thresholds for offsets in each direction. We identified significant differences between certain directions, with close offsets being more sensitive than right and left offsets, which were then more sensitive than up, far, and down offsets. The smallest threshold we determined was for close offsets at 7.8 centimeters, while the largest was for downward offsets at 13.4 centimeters. Next, we examined the effects of offsets on target selection. First target selection time was discarded, and the remaining 7 were examined during analysis. We found positive correlations between magnitude and target selection time for each direction, which can be indicated and seen by the generally positive trend observed in the graph to the left. We also compared target selection time for offsets based on our estimated thresholds. So if the offset was 0, if there was no offset applied, if it was below the threshold for the corresponding direction, or if it was exceeding the threshold for the corresponding direction. Offset magnitude and direction were only significantly related to selection time if the magnitude was beyond the threshold for the direction. And while a significant difference was identified, the overall effect of our largest magnitudes on the selection time was still quite small, at less than 1/4 of a second on average. Looking more into our thresholds, our findings show that similar thresholds exist for paired offsets along each axis. So right and left along the x-axis, up and down on the y-axis, and then close and far along the z-axis. However, this did not hold for the z-axis, where we can see that close and far offsets were significantly different. Difference may be due to extra physical movement needed to reach targets in front of you while your hand is positioned closer to your body. But this is still representative of some situations where your hands may be remapped, such as those cases in haptic retargeting, where the physical prop may be further away than the virtual object. Then additionally, while we did not control for participant handedness, we did not observe a difference in left or right thresholds, which suggests this may not be a factor in detection. However, future work should more critically examine the role of handedness in techniques where direction is a factor, because in general, most participants will be right-handed if you're not specifically recruiting left-handed participants. Notably, even our largest threshold that we estimated is still quite small. It's about the size of one hand. It is likely that in some cases, this distance is going to limit certain techniques to a point where you're only going to be extending a user's reach a small amount. And future work should examine using positional limits to other techniques to better understand how they can be applied to create more natural and undisrupted interaction techniques. To conclude, our work provides detection threshold estimates for fixed offsets in 6 different directions. We found that if the user's hand was kept within the threshold, they performed similarly to unmodified hands, with only a small trade-off if the hand was exceeded beyond the threshold. And overall, these findings are providing guidelines for how far hands can be moved before they are detectable, or before user performance begins to suffer while their hand is displaced from their virtual hand is displaced from their real hand. Thank you for listening to the presentation. I would like to thank my co-authors for the contribution to this work. And if you're interested in learning more about this work, more information is in the full paper. And if you'd like to contact me about this work, my email is listed on this slide. Thank you.
Okay, Brett, thank you so much for your nice presentation. And I think there's a question coming up. So Paul Glumeau is asking, how did you prevent users from leaning forward to extend their reach?
That's a very good question. We had this calibration step at the beginning of each experiment, and we positioned the targets a constant distance away from each participant in order to keep that consistent. We also would frequently throughout the experiment tell them to line back up on this physical spot in our tracking space in order to keep them from sort of drifting as they moved. And for leaning, we did not prevent them from leaning because this sort of physical response needed to reach a target is still kind of representative of how people would have to move under certain sets of these different offsets. So we did not specifically account for that.
Okay, thank you so much. Just looking if there are more questions. If not, I have a couple of questions for you. So I guess you used a specific controller, the Oculus controller, which also let's say imposes a certain hand pose, right? So
yes.
the user grabbed the controller in a specific way. And can you speculate a little bit if you think the results would change if different initial hand poses or orientations would have been used? That's maybe question number one. And related to that, might this offset also be, let's say, substantially different if you would use other input tools, either only the bare hand, a different controller, or a stylus? Could you give us some speculation about that, some hints?
Yes, that's another great question. We did use the default Oculus controllers in our experiment, and the actual hand that was seen by the users was the corresponding model for the controller. So that was matching up with what they were feeling they were doing and holding with their controller. And future work, we've definitely been considering actually applying kind of study methodology to different types of inputs, like using a glove to actually track and let people move their hand without a controller. And I would suspect that having a higher kind of fidelity between the user's hand and the model they see could even make these thresholds a little stricter than the ones that we propose when people are holding a controller.
Okay. So thank you for answering that. There's another question from the audience. Now the questions are coming very good by Steve Feiner, and he's interested in if you also have looked into orientation offsets, or if you're planning to do that. He states the example similar to how a mouse cursor moves in the plane rotated relative to the one in which the mouse moves. So have you looked in orientation offsets, or do you plan to do that?
We have not considered that sort of offset yet. Our next step, whenever we can get back to sort of running VR studies in our lab, would be to looking at the sort of combination of like scaling movement as well as offsets, and looking at if either one of those techniques sort of dominates the other in terms of direction. But I guess these rotational offsets could be worth investigating as well at some point.
Okay. And maybe a last question. I mean, now we know that we have, let's say, a very small amount of offset that we can tolerate, about 10 centimeters, yeah, plus minus a few centimeters to either side. And I think you also already started to talk a little bit about it in your discussion, in your conclusions. Are there any ways, do you see any ways to increase that offset with or without dynamic haptic retargeting, with or without triggering the perception when moving the hand?
I think our offsets are probably a little more conservative than those that you may experience if you are actually participating in some immersive environment, because our task is very focused on this is exactly what you're doing. But providing sort of multitasking or actually like giving the user some sort of entertainment or practical assignment for them to focus on something else will probably make them a little more tolerant of not just this sort of hand remapping, but other techniques as well.
Okay, great. Then, Brett, thank you so much for your talk. And also thanks to all the presenters who have been active in the session. So let's give all the presenters a hand. Thank you so much. Great, thank you. And this concludes the session. And I think we will have a 3 hours break by now. And in the afternoon, we will have another keynote. But I think, Francisco, you will tell us more about that.
Great, Jens. Thanks a lot. Congratulations for you and the authors. This great session. Thanks a lot. Yeah, indeed, we are going to have in 4 hours from now a keynote from Paul de Bevec. Also, we are closing this session of this morning here, Brazilian time. And we have some announcements for social activities and some suggestions for you to enjoy during this day with the student volunteer, Tiago Chaves. Tiago, please come. Thanks a lot, everyone. See you later.
Thank you, Francisco, and hello, everyone. I would like just to invite you all to explore the world here, this virtual world, especially the beach, the Porto de Galinhas beach, where you can find some coffee areas where you can sit and chat and get to know each other a little bit more. I think that would be nice. You can also go to the Recife Gallery, and there are a bunch of pictures and videos showing the Recife culture, which is very rich. So it will be nice if you guys check it there. And meanwhile, while there's no session going on, and that's it. Just inviting you all to explore all the things we prepared for you very much, and enjoy.